Hello, ladies and gentlemen, this is Miss Skokin. We're in the last section of Chapter 5, Section 8, Applying Special Right Triangles. Our objectives are justify and apply properties of 45-degree, 45-degree, 90-degree triangles, and justify and apply properties of 30-degree, 60-degree, 90-degree triangles. Vocabulary, special right triangle, 45, 45, 90 triangle, and 30, 60, 90 triangle. You got 4 warm-up questions to get you started on this lesson. So pause the video, work on the questions, and turn the video back on when you are ready to check your answers. These questions are throwbacks to some of the algebra skills that you learned last year. As always, if you have a question about any of these, bring them to class. By drawing a diagonal segment of length y, we could cut a square with side length x in half. We know that a square has 4 right angles. I'm just going to draw 2 of them in here. So if we look at these 2 as separate triangles, then both of these triangles could be classified as right triangles. We also recognize that with a square, all 4 side lengths are exactly the same. So when we look at the 2 halves of the square as 2 triangles, we also recognize that these are going to be isosceles triangles. So 2 different classifications, one by angle, the other one by side length. Now, what would those angles measure? Well, we already said that the corners, the 4 corners of the square, measure 90 degrees each. So when we bisected the angles, we ended up with 2 45-degree angles on both sides. So the angles would measure 45 degrees, 45 degrees, and 90 degrees. You can see the 3 angles on each of those triangles is exactly as we've listed it, 45, 45, and 90. Last of all, we want to know what these side lengths would measure. And the first 2 legs of the right triangle would measure x and x. Now, we have this y. We don't know how much y is, but let's see if we can figure something out using the Pythagorean theorem. The c squared equals a squared plus b squared is going to turn into, c squared is y squared, a is x, so we have x squared, and then we have b, which, because this is an isosceles triangle, is also x squared. We combine like terms, and we have 2x squared is equal to y squared. And then we're solving for y, so we're going to take the square root of both sides, and we're going to end up with y equals square root of 2 times square root of x squared, which we know is just x, so that's going to be y equals x times the square root of 2. That brings us to theorem 5-8-1, the 45, 45, 90 triangle theorem. And it says, in a 45-degree, 45-degree, 90-degree triangle, both legs are congruent, and the length of the hypotenuse is the length of the leg times square root of 2. Now, this is what we just demonstrated by using the Pythagorean theorem and cutting a square in half. Because this relationship is consistent, and because this is from cutting a square in half, we're going to call that 45, 45, 90-degree triangle a special triangle. In example 1 on the next page, we're going to practice finding missing side lengths on the 45-degree, 45-degree, 90-degree triangle. Example 1 says find the value of x and give your answer in simplest radical form. That means you're not going to get an irrational number and put it in your calculator. So first things first, we recognize that this is a 45-degree, 45-degree, 90-degree triangle, and we remember that that means that we've got an isosceles triangle. We're going to label the hypotenuse and the legs, and then we're going to recall the information that we got about the relationship in the 45, 45, 90 triangle theorem. And that is that the hypotenuse's length is the square root of 2 times the length of the leg. So we substitute in x for the length of the hypotenuse and 8 for the length of the leg. And so we know the length of the hypotenuse is 8 times the square root of 2. In question B, we've got another right triangle. Again, it's isosceles, and again, that means it has to be a 45 degree, 45 degree, 90 degree right triangle. We're going to label the hypotenuse and the legs, and then we're going to remember once again the relationship that the length of the hypotenuse is equal to the length of the leg times the square root of 2. Next, we substitute in the hypotenuse length, which we were given in the question. And then we see that we're going to need to divide both sides by the square root of 2 to solve for the leg length. So we end up with the leg length is equal to 5 divided by the square root of 2. But we remember that we need to rationalize that denominator. We learned that in Algebra 1. And that is because we can't have any radicals in the denominator. So we're going to end up with 5 times the square root of 2 over 2 as the value of x, which is the leg length on our triangle. You know what's coming next. Then now you try questions for you to work on. Turn the video back on when you're ready to check your answers. Both of these questions were pretty straightforward, and I'm sure you didn't have any trouble with them. We've got in example 2 a real world application for our 45, 45, 90 triangle. Let's start by reading the question. Jana is cutting a square of material for a tablecloth. So we're starting with a square. The table's diagonal is 36 inches long. We know that that's going to end up being the hypotenuse. She wants the diagonal of the tablecloth to be an extra 10 inches long, so it will hang over the edges of the table. So that's going to add to our hypotenuse length. What size square should Jana cut from the fabric to make a tablecloth? And then we're going to round to the nearest inch. Let's draw a square so we can see what's actually happening. The side of the square, the length of the side of the square is what we're actually trying to find. So I'm just going to put X in for that. We also know that all 4 sides of the square are the same. So I'm going to put our tick marks in. And next, I'm going to draw the diagonal across the square. I'm going to color in the bottom part of the square because it's just easier for us to see it as a triangle instead of as looking at it as a square. Okay, next item, let's go ahead and put in what the diagonal length is supposed to be. We know it started out as 36 inches, but we also know it's going to be 10 inches longer than that, so it can hang over the edges of the table. So it's going to be 46 inches long. This is a perfect place for us to include the relationship that we know between the leg and the hypotenuse of a 45, 45, 90 triangle. So we've set it up. Let's plug in the 46 that we know about. Remember, the leg we'll call x. That's what we're solving for. At this point, we know we need to divide both sides by the square root of 2. Now, just a reminder, this is a real-world example. So this is something we're going to put into our calculator because we want to be able to round to the nearest inch. So we put 46 divided by the square root of 2 into our calculator, and we get to the nearest inch that our tablecloth needs to be made of a square 33 inches on each side. In general, I know word problems is not anybody's favorite thing to do, but you have to admit this one was pretty straightforward. Most of them usually are if we take the time to read them carefully. Before we talk about Theorem 5-8-2, let's take a look at an equilateral triangle. So we start out with an equilateral triangle. You can see the 3 tick marks. Just a reminder, equilateral triangles are also equiangular, so each of the 3 angles measures 60 degrees. Now I'm going to designate the side length as 2x. So all 3 of these are going to measure 2x. But before I write it on the third side, I'm going to slice this equilateral triangle in half. And what that means is I just split my 2x into an x and an x. So I still have my equilateral triangle. I split it into two triangles. And when we consider that the top 60-degree angle was also split in half, we know that each one of these two smaller angles measures 30 degrees. So what we ended up having is a 30-degree, 60-degree, 90-degree right triangle. The lengths of the three sides of the right triangle, let's just talk about the green one for right now. The short leg measures x. The hypotenuse measures 2x. And then we have the long leg, which at the moment we don't have it labeled. I'm going to call it y, and then we're going to figure out, using the Pythagorean theorem, what that length y actually is. Let's start by writing the Pythagorean theorem. C squared is equal to a squared plus b squared, and let's plug in what we know. The hypotenuse length is 2x, so that's going to be 2x squared. One of the legs is x, so that'll be x squared, and the other one we'll just call y. When we square 2x, we end up with 4x squared, and we're going to be solving for y squared. So I'm going to rearrange this as 4x squared minus x squared equals y squared. And now I'm going to reverse those two sides to give myself a little bit more space. So y squared is equal to 3x squared when we combine like terms. We take the square root of both sides and we end up with y is equal to the square root of 3x squared. We know that that squared x can come out of the radical, and we're going to end up having y is equal to x times the square root of 3. Now remember, x was the length of the short leg. So now we have a relationship that relates the length of the short leg, the long leg, and the hypotenuse of a 30, 60, 90 degree triangle. This is another triangle that we're going to call a special triangle, just like the 45, 45, 90 triangle. Our theorem says in a 30 degree, 60 degree, 90 degree triangle, the length of the hypotenuse is 2 times the length of the shorter leg, and the length of the longer leg is the length of the shorter leg times square root of 3. This is what we've just demonstrated by cutting our equilateral triangle in half. Let's take a look now at an example 3, and we're going to use our 30, 60, 90 degree theorem to solve for the missing values of x and y. Let's start by labeling our triangle. We know that this is the hypotenuse. We also know that this is the short leg, and this one is the long leg. Now let's recall what the relationship is, where the short leg equals x, the long leg is equal to x times the square root of 3, and the hypotenuse is equal to 2x. If the hypotenuse is equal to 2x, and the length of the hypotenuse given to us in the diagram is 22, then we know that in order to find x, we have to divide 22 by 2, and we end up with x is equal to 11. So we have the length of the short leg and the length of the hypotenuse. All we need is the length of the long leg. And we're going to find that by multiplying the length of the short leg by square root of 3. So 11 square root 3 is the length of the long leg. So we found the length of x and y, but more importantly, we found the lengths of the sides of the triangle. Now we have question B. Again, we have a 30, 60, 90 triangle, so we're going to label our short leg, our long leg, and our hypotenuse. This time we were given the length of the long leg. So the long leg is 15, and we know that that is going to be equal to x times the square root of 3, x being the length of the short leg. So in order to find x, we need to divide both sides by the square root of 3. And then we need to rationalize that denominator. So 15 over square root of 3 times square root of 3 over square root of 3 is going to give us 15 root 3 over 3. That, of course, can be simplified because 3 goes into 3 once and goes into 15 5 times. So the length of the short leg is 5 times the square root of 3. We already had the length of the long leg given to us in the diagram, and that was 15, so now we just need to find the length of the hypotenuse. And we remember that the hypotenuse is equal to 2 times the length of the short leg. So that's going to be 2 times 5 square root 3, or 10 root 3. So we've got all 3 legs. The short leg was our unknown x, and the length of the hypotenuse was our unknown y. Okay, now we've got a few for you to try. So you're going to work on these and then turn the video back on when you are ready to check your answers. In question A, we were given the hypotenuse and needed to find the lengths of the short leg and the long leg. In question B, we were given the length of the long leg and we had to find the lengths of the short leg and the hypotenuse. Neither of these was very difficult, but it is a big flashback to our algebra work. So if you do have any questions about that, you may want to take the homework practice pretty slowly and carefully, showing all your steps to make sure that you're able to work backwards to find whichever length is missing. Now let's take a look at example number 4. In example number 4, we have a clock, and it says the frame of the clock shown is an equilateral triangle. The length of one side of the frame is 20 centimeters. Will the clock fit on a shelf that is 18 centimeters below the shelf above it? So, of course, the first thing to do once we have kind of deconstructed what the words are saying is to label our triangle. And we remember about the 30, 60, 90 triangle. That's exactly what we're ending up having here, because we took that 60, 60, 60 or equilateral triangle and we split it. And that vertical height, we're trying to figure out if it's 18 centimeters or taller, we know, or 18 centimeters or less, it's going to fit under the shelf. And if it's taller than that, it's not going to fit under the shelf. So a few other things that I'm going to add on here. We know that if the equilateral triangle side length is 20 centimeters, then each of these halves is going to be 10 centimeters. And another thing, as we look at half of this equilateral triangle, we look at the right triangle, we can see that the short leg is this 10 centimeter leg. The hypotenuse is the 20 centimeter length, side length, and this hypotenuse is 2x, the short is x, and then the long leg is this orange one that I've drawn, and we want to see how tall that is, but we know it's going to have the relationship of x times the square root of 3. We've marked up the diagram pretty well. Now let's organize the information that we've learned. So we know the length of the short side and we know the length of the hypotenuse. The length of the long side is going to give us the height of the clock. And for that, all we need to do is to plug in x. So it's going to be 10 root 3 centimeters. Now, while this is a great number, this isn't really an easy number to compare to 18 centimeters. So we're going to put this into our calculator and we're going to get approximately 17.3 centimeters. Since the clock is 17.3 centimeters tall, we know that it will fit on the 18 centimeter shelf. So we're good to go. There's a now you try for you to work on, and so you are going to pause the video, work on this, and then turn the video back on when you are ready to check your answer. This is the last example before you can get started on your independent practice. Once again, this question was pretty straightforward, and now that we're done with our taking notes and the examples for this section, it is time to get started on your independent practice. As always, if you have questions, be sure to bring them to class.